Hydrocarbons are organic compounds containing only hydrogen and carbon. They play an important role in our life as they meet more than 90% of the energy requirements of the world. Also, they are the major sources of various other organic compounds which we use in different walks of life. Coal and petroleum are complex mixtures of hydrocarbons. Coal tar, a product of destructive distillation of coal, when subjected to fractional distillation, produces various aromatic compounds including benzene. These compounds are used in the preparation of various industrially useful products such as polymers like polystyrene, dyes, drugs, etc. Petroleum, on the other hand, is a major source of alkanes and cycloalkanes. When it is subjected to fractional distillation, the various fractions obtained are used as fuels for different purposes. For example, natural gas in the form of CNG, that is, compressed natural gas, and LNG, that is liquefied natural gas, are used as automobile fuels. Liquefaction of petroleum gas renders a very useful domestic fuel in the form of LPG. Kerosene oil is also used as a domestic fuel, but it is more polluting as compared to LPG. Petrol and diesel are also used as automobile fuels. Among the automobile fuels used, CNG or LNG are the clean fuels. That is, these are non-polluting fuels. Other higher hydrocarbons are used as lubricants, solvents for paints, and so on. Hence, we can say that the hydrocarbons act as sources of energy. Now, let us look at the classification of hydrocarbons. On the basis of carbon skeleton, that is, the type of carbon-carbon bonds, hydrocarbons can be classified into three main categories: saturated, unsaturated, and aromatic hydrocarbons. Saturated hydrocarbons are the hydrocarbons consisting of carbon-to-carbon single bonds. Saturated, open-chain or acyclic hydrocarbons, in which carbon atoms are linked by straight or branched chains, are called alkanes. The general formula for alkanes is CnH2n plus 2, where n is equal to the number of carbon atoms present. For example, propane. Saturated hydrocarbons in which the carbon atoms join together to form a closed chain are called cycloalkanes. The general formula for cycloalkanes is CnH2n, where n is equal to the number of carbon atoms present. For example, cyclopropane. Unsaturated hydrocarbons consist of one or more carbon-to-carbon multiple bonds. That is, a double bond or a triple bond or both. Unsaturated, open chain or acyclic hydrocarbons in which carbon atoms are linked by straight or branched chains containing at least one carbon-to-carbon double bond are called alkenes. The general formula for alkenes is CnH2n, where n is equal to the number of carbon atoms present. For example, propene. Unsaturated, open chain or acyclic hydrocarbons in which carbon atoms are linked by straight or branched chains containing at least one carbon-to-carbon triple bond, are called alkynes. The general formula for alkynes is CnH2n-2, where N is the number of carbon atoms. For example, propyne. Aromatic hydrocarbons are cyclic hydrocarbons with alternative double bonds in conjugation. Aromatic compounds are benzene and the compounds that resemble benzene in their chemical behavior. For example, benzene, toluene, etc. As we learnt, alkanes are the simplest form of hydrocarbons containing carbon-carbon single bonds. Its molecules consist of carbon-hydrogen bonds and carbon-carbon single bonds. Since each carbon is bonded to 4 other atoms through single covalent bonds, the compounds are called saturated compounds. They contain carbon-carbon single covalent bonds which are strong sigma bonds. Due to this, the compounds are almost chemically non-reactive at normal temperature and pressure. This is why they were earlier known as paraffin, which, in Latin, means little affinity. We have learnt that the general formula for alkanes is CnH2n+2, where N stands for the number of carbon atoms and 2n+2 stands for the number of hydrogen atoms in a molecule. The most simplest alkane is methane. It has one carbon atom connected to 4 hydrogen atoms. The next member, ethane, can be obtained by replacing one of the hydrogen atom of methane by the CH3 group. This group is methyl group, which is a type of alkyl group. Thus, ethane with molecular formula C2H6 is derived by replacing one hydrogen atom by CH3 group from the methane CH4 molecule. Similarly, an entire series can be obtained by replacing one hydrogen with the CH3 group. There is no limit to the number of carbon atoms that can be linked together. However, as the number of carbon atoms within a molecule goes on increasing, the structure becomes more and more complex. When a carbon atom is attached to hydrogen or just one other carbon atom, it is said to be primary carbon. When a carbon atom is attached to 2 other carbon atoms, it is said to be secondary carbon. When a carbon atom is attached to 3 carbon atoms, it is said to be tertiary carbon. And when all the bonds formed by a carbon atom are with 4 other carbon atoms, it is said to be neo or quaternary carbon. In a molecule, the terminal carbon of a carbon-carbon chain is always attached to 1 carbon and 3 hydrogen atoms, and hence it is called primary carbon atom. The first 3 alkanes in the series, methane, ethane and propane, only have 1 molecular structure. However, as the number of carbon atoms in an alkane goes on increasing, we get more than one structural arrangement for a particular molecular formula. Such compounds are called isomers. The phenomenon of exhibiting isomers is called isomerism. For example, in butane, we get 2 possible structures, one as a continuous chain and the other branched. Now, although the chemical formula for all these structures is the same, their properties differ due to the differences in their carbon chain structure. Such compounds are called chain isomers. In pentane, we get three possible structures. 1. A continuous chain with secondary carbon atoms. Another with one tertiary carbon atom, and the third with neo or quaternary carbon atoms. Here, the structural isomers differ in the carbon chain structure and hence are called chain isomers. The table here gives the number of isomers present for a given molecular formula. Butane has 2 isomers and pentane has 3. Similarly, as the number of carbon atoms goes on increasing, the number of structural isomers goes on increasing. We come across many groups like CH3, C2H5 attached to carbon atoms. These groups are derived by removing one hydrogen atom from alkanes and are known as alkyl groups. Their general formula is CnH2n plus 1. The name of the alkyl group is derived from name of the parent alkane by replacing suffix ane of alkane with yl. We have learnt that the properties of a compound depend upon the structure of the compound. However, these compounds have the same molecular formula. So, how do we differentiate between them and how do we decide their names? To address the issue, the International Union of Pure and Applied Chemistry, or IUPAC, has come up with standard rules for naming compounds. The key steps to label a structure are: identify the longest continuous chain of carbon atoms. Name this longest parent carbon chain using standard naming rules. Add the name of each side chain before the name of the parent carbon chain. Number the parent carbon chain so that the sum of the members assigned to each substituent will be a least number. Write the name of the side chain with its number before as prefix to the name of the root word of the parent carbon chain. If there are multiple side chains of the same type attached to the parent carbon chain, use prefixes such as di and tri to indicate it with its assigned number to the parent chain. Let's again look at the 3 structures that we had obtained for pentane, C5H12, and label them as structure 1, 2, and 3. Now, first identify the longest continuous chain of carbon atoms. Structure 1 contains 5 carbon atoms. Structure 2 contains 4 carbon atoms. And structure 3 contains 3 carbon atoms in the parent carbon chain. Next, name this longest parent carbon chain using standard naming rules. This name for structure 1 is pentane, structure 2 is butane, and structure 3 is propane. Since structure 1 doesn't have any branches, its name is pentane. Now, in structure 2 and 3, add the name of each side chain before the name of the root chain. So, in structure 2, we add methyl before butane, and in structure 3, we add methyl before propane. Now, number the parent carbon chains so that the sum of the numbers assigned to each side group will be least. In structure 2, the carbon atoms are numbered 1 to 4 with the substituent alkyl group at carbon atom number 2. In structure 3, the carbon atoms are numbered 1 to 3 with both the substituent alkyl groups attach to carbon atom number 2. Then, number and name the side chains and write as prefix to the name of the parent carbon chain. With this, we have named structure number 2 as 2-methylbutane. However, structure 3 has multiple side chains of the same type of carbon atom number 2. So, we take the 6th step, which is to use prefixes such as di and tri to indicate the groups and number each one in the name. Thus, the name of the third compound is 2,2-dimethylpropane. With this, we have labeled all the 3 structures. Just like it's important that we know how to write correct IUPAC names for a compound given its structure, we also need to be able to draw the structure given its IUPAC name. The key steps to draw a structure from a given name are: draw the chain of carbon atoms from the molecular formula. Number the carbon atoms within the parent carbon chain. Attach the substituent alkyl groups given as prefix in the name to the carbon atoms as specified in the numbering. Satisfy the remaining valence of each carbon atom by putting the requisite number of hydrogen atoms. Let us now try and draw the structure of 3-ethyl-2,2-dimethylpentane. First, from the base name, pentane, we can deduce that the parent carbon chain contains 5 carbon atoms. Second, number these carbon atoms. Third, from the name we can identify that we have to attach an ethyl group to atom number 3 and 2-methyl group to atom number 2. Fourth, fill in the remaining places with hydrogen atoms such that each carbon atom fulfills its valence of 4. Alkanes can be obtained in a laboratory either from unsaturated hydrocarbons, alkyl halides, or carboxylic acids. Let's look at each one in detail. Unsaturated hydrocarbons, like alkenes, react with hydrogen in the presence of finely divided catalysts, like platinum, palladium, or nickel, to form alkanes. As this reaction involves addition of hydrogen, it is called hydrogenation. The surface of these metals absorb hydrogen gas and activate the hydrogen-hydrogen bond. The reaction using platinum and palladium can be catalyzed at room temperature. However, the reaction using nickel as a catalyst requires relatively higher temperature and pressure. For example, ethene on hydrogenation in presence of catalysts such as finely divided platinum, palladium, or nickel gives ethane. To obtain alkanes from alkyl halides, we can either use the reduction method or the Wurtz reaction. Alkyl halides on reduction with reducing agents such as zinc-copper couple in ethanol or zinc and dilute HCl gives alkanes. For example, ethyl iodide, when reduced by using zinc-copper couple in ethanol or zinc and dilute HCl, gives ethane. Now let's see how to obtain alkane from alkyl halides using the Wurtz reaction. Alkyl halides on treatment with metallic sodium in presence of dry ether give higher alkanes with even number of carbon atoms. This reaction is known as Wurtz reaction. For example, the reaction of bromomethane with sodium metal in presence of dry ether gives ethane. It is important to note that when two different alkyl halides are taken, then a mixture of alkanes is produced. For example, the Wurtz reaction of mixture of methyl iodide and ethyl iodide forms ethane, butane, and propane respectively. As alkanes have close boiling points, it becomes very difficult to separate them from the mixture. Hence, this method is not suitable to prepare the alkanes with odd number of carbon atoms. Now, let's see how alkanes can be prepared from carboxylic acids. Sodium salts of carboxylic acids on heating with soda lime give alkanes with one carbon atom less than the parent carboxylic acid. Soda lime is a mixture of calcium oxide and sodium hydroxide. As this reaction involves the elimination of carbon dioxide from a carboxylic acid molecule, the process is known as decarboxylation. For example, sodium propionate on heating with soda lime gives ethane. Coal-based electrolytic method is yet another method to prepare alkanes from carboxylic acids. This method involves the preparation of alkanes with even number of carbon atoms through the electrolysis of aqueous solutions of sodium or potassium salts of carboxylic acids. For example, the aqueous solution of sodium or potassium acetate on electrolysis gives ethane. The mechanism of the reaction can be understood through the following steps. At anode, the acetate ions in the solution lose electrons at the anode and form acetate free radicals. The acetate free radical lose carbon dioxide molecule and thus form methyl free radicals. The methyl free radicals further react and form ethane gas. At cathode, water molecules accept the electrons and split up into hydroxyl ions and hydrogen free radicals. Two such hydrogen free radicals combine together and form hydrogen gas. Thus, in coal-based electrolysis method, alkane is produced at the anode. First, let's look at the physical properties. These include appearance, color, odor, boiling point, solubility, and polarity, among others. These properties depend on the attractive forces working on the molecules. As we have learned, alkanes consist of only carbon-to-carbon and carbon-to-hydrogen single bonds. These bonds are covalent, and the electronegativity between two carbon atoms or between carbon and hydrogen is almost negligible. Hence, the molecules formed are non-polar. This is why the only attractive force acting on these molecules is the weak van der Waals forces. Therefore, the first four members of the series, C1 to C4, are gases. C5 to C17 are liquids, while the molecules containing 18 or more than 18 carbon atoms are solids at 25 degrees Celsius. They are all colorless and odorless. Due to their non-polar nature, these compounds are insoluble in polar solvents like water and soluble in non-polar solvents like benzene. Their boiling point is decided by the strength of the van der Waals force. This force is very sensitive to distance. Hence, for a strong force of attraction, the molecules need to be held close together. However, in alkanes, because of their nonpolar molecules, the van der Waals forces are weak, and hence their boiling points are much lower than expected. As the size of a molecule increases, its surface area increases. Thus, the strength of the intermolecular van der Waals force also increases. A linear or straight chain alkanes like pentane has a higher boiling point than its branched isomers like 2-methylbutane and 2,2-dimethylpropane. This is because branching reduces the surface area of a molecule, leading to a weakening of the van der Waals forces, which are then overcome at relatively lower temperatures. Now, let's look at the chemical properties of alkanes. As we have seen, alkanes are nonpolar. Their carbon bonds are quite stable, and so they do not easily react with acids and bases. However, they do undergo substitution reactions and combustion reactions under certain conditions, as their carbon atoms are in strongly reduced states. During this reaction, the hydrogen atom of an alkane is substituted, and hence the reactions are called substitution reactions. When the element substituting the hydrogen is a halogen, the reaction is called halogenation. It involves 3 steps: initiation, propagation, and termination. Let's go through each step by observing the chlorination of methane. During chlorination of methane, the 4 hydrogen atoms of methane are step by step substituted or replaced by chlorine atoms, forming tetrachloromethane as the final product. During initiation, the chlorine molecule is homolyzed in the presence of heat or light, forming chlorine-free radicals. During propagation, 2 reactions take place. First, the chlorine-free radical attacks the methane molecule, forming a methyl-free radical and hydrogen chloride. Next, the methyl-free radical attacks the second chlorine molecule, forming chloromethane, and one more chlorine-free radical, setting up the chain reaction. The chlorine-free radical formed sets up many other propagation steps to form more halogenated products. These steps are repeated till all the hydrogen atoms in the methane molecule are replaced by chlorine atoms. During termination, the reaction stops either because all the reactants have been consumed or because of the following possible chain terminating reactions. One possible reaction is that 2 chlorine-free radicals combine to form a chlorine molecule. Another possible reaction is that 2 methyl-free radicals combine to form ethane. Or a chlorine-free radical and a methyl-free radical combine to form chloromethane. Thus, in the chlorination of methane, ethane is obtained as a byproduct. Now let's understand the combustion reaction of alkanes. On heating, alkanes get completely oxidized to carbon dioxide and water along with heat. In the presence of air or dioxygen. This is why alkanes are used as fuels. When alkanes undergo incomplete combustion, they form carbon black. It is used in the manufacturing of ink, printer ink, black pigments, and as filters. Alkanes, like methane, on heating at high pressure with a regulated supply of oxygen and in the presence of a suitable catalyst, provides a variety of products like methanol and methanal. Ethane gives ethanoic acid, and an alkane with tertiary hydrogen atom like 2-methylpropane gives corresponding alcohol. When a normal alkane like N-hexane is heated in the presence of anhydrous aluminium chloride and hydrogen chloride gas, it isomerizes to a branched chain alkane like 2-methylpentane and 3-methylpentane. Alkanes undergo aromatization or reforming. That is, a normal alkane with 6 or more than 6 carbon atoms like N-hexane, when heated to 773 Kelvin at 10 to 20 atmospheric pressure in the presence of a catalyst like oxides of vanadium, molybdenum or chromium supported over alumina, gets dehydrogenated to form cyclic compounds like benzene or its homologues. Alkanes also react with steam. This reaction is used in the industrial preparation of dihydrogen gas. For this, methane is heated at 1000 degrees Celsius in the presence of nickel, along with steam to form carbon monoxide and dihydrogen gas. Higher alkanes at higher temperatures decompose to form lower alkanes and alkenes, amongst others. This reaction is also known as pyrolysis, or alkanes with 2 or more carbon atoms like ethane and propane consist of carbon-to-carbon single covalent sigma bonds, in which the electrons are shared symmetrically around the internuclear axis of the carbon-carbon single bonds. The atoms within a molecule are in constant rotational movements along the internuclear axis, as the molecular orbitals are not disturbed due to rotation. Due to this, the shape of an alkane molecule can be twisted into different three-dimensional arrangements by rotation about the carbon-to-carbon single bond or bonds. These different three-dimensional arrangements are interchangeable and are called conformations. These interconversions are very rapid, and hence, in a short span of time, a given molecule may exist in infinite different conformations. However, remember, conformations do not affect the bond angle and the bond length. Now let's understand the concept of conformation better by using the ethane molecule as an example. We can see that each carbon atom is attached to 1 carbon and 3 hydrogen atoms. Now, imagine one of the carbon atoms along with its hydrogen bonds rotating around the internuclear axis of the carbon-to-carbon bond. You can see that this rotation causes infinite different spatial arrangements of the hydrogen atoms of 1 carbon atom with respect to the hydrogen atoms of another carbon atom. These arrangements are called conformational isomers. In reality, both the carbon atoms will be going through such rotations, thus increasing the number of spatial arrangements. Let's study these in detail. We can observe that there are 2 extreme positions of the hydrogen bonds of 1 carbon in relation to the hydrogen bonds of another carbon atom. One where the hydrogen atoms attached to the two carbon atoms are as close as possible to each other, and the other where they are as far apart as possible. When the arrangement has the hydrogen atoms close to each other, the three hydrogen atoms and carbon atoms at the back are hidden by the three hydrogen atoms attached to the carbon atom in the front. And so the arrangement is known as eclipsed conformation. The arrangement wherein the hydrogen atoms are far from each other, the three hydrogen atoms and carbon atoms at the back are visible behind the three hydrogen atoms attached to the carbon atom in the front, giving the arrangement a neatly distributed look. And so the arrangement is known as staggered conformation. All the arrangements between the eclipsed and staggered positions are known as skew conformations. In the eclipsed conformation, the molecule is the least stable as the repulsive force between the electrons is the maximum. This is due to close spatial arrangement of the carbon-hydrogen bonds. In the staggered conformation, the molecule is the most stable, as there is minimum repulsive force between the electrons. This is because the carbon-hydrogen electrons are the farthest from each other. The repulsive interaction between the electron clouds in a molecule, which affects the stability of a conformation, is called torsional strain. Its magnitude depends upon the angle of rotation about the carbon-to-carbon bond. This angle is known as torsional or dihedral angle. The energy difference between eclipsed and staggered conformations is 12.5 kilojoules per mole, which is easily overcome at room temperature and pressure. Due to this, it is not possible to separate different conformation isomers of ethane. Now that we have seen what conformation means, let's learn the two standard visual representations used to explain it. These are known as sawhorse projection and Newman projection. In sawhorse projection, the molecules are viewed along their molecular axis, that is, at an oblique angle. Here, the carbon-to-carbon bond is shown as a long straight line, whose upper end is bent slightly either towards the left or towards the right-hand side. The front carbon is shown at the lower end of the line and the back carbon at the upper end. Each carbon has 3 hydrogen atoms attached to it. These bonds are shown with the help of 3 lines attached to the carbon atom. These are inclined at an angle of 120 degrees to each other. Using sawhorse projection, the 3-dimensional structure of the eclipsed and staggered conformations can be easily visualized. In Newman projection, the carbon-to-carbon bond conformation is viewed head-on, that is, front to back. The carbon atom at the front is represented as a dot and the carbon atom at the back is represented as a circle. The hydrogen atoms attached to the carbon atoms are shown by lines. The bond angle between these lines is kept at 120 degrees. The hydrogen atoms connected to the carbon atom in the front are represented by longer lines, and those connected to the carbon atom at the back are represented by shorter lines. Using Newman projection, an unsaturated hydrocarbon with a double bond in between the carbon atoms is called an alkene. Alkenes are also called olefins, which means oil forming, as its first member, ethene, on reacting with chlorine, forms an oily substance. As you have studied, a carbon-to-carbon double bond consists of one strong sigma bond and one weak pi bond. A sigma bond is formed due to the head-on overlap between two sp2 hybrid orbitals of two carbon atoms, whereas a pi bond is formed due to the sideways overlap between two pure 2p orbitals of two carbon atoms. Due to the presence of a double bond, an alkene has two hydrogen atoms less than corresponding alkane. Hence, the general molecular formulae of alkenes is CnH2n. The pi bond, which consists of loosely held delocalized pi electrons, serve as a source of electrons for the electron-seeking reagents. Thus, the electron-seeking or electron-deficient reagents, called electrophilic reagents, attack weaker pi bond in alkenes and form corresponding saturated compounds. The presence of the weaker pi bond makes alkenes more reactive than the corresponding alkanes. The IUPAC name of the alkenes can be divided into two parts, that is, root word, which indicates the length of the carbon chain, and suffix -ene, which indicates the double bond. For example, the IUPAC name of an alkene with two carbon atoms can be divided into two parts, that is, root word eth plus the suffix -ene. Hence, the IUPAC name is ethene. In the IUPAC system, alkenes are named by replacing the suffix -ane of the corresponding alkanes by the suffix -ene. For example, ethene is named from ethane by replacing the suffix -ane with -ene. For alkenes with more than 3 carbon atoms, the carbon with a double bond is given the least number, and the number is indicated in the name. For example, but1-ene, but2-ene. An alkane with an alkyl group as a substituent is numbered in such a way that carbon with double bond gets least number. While naming, the number of the carbon atom with the substituent and the name of the substituent, that is alkyl group, is written as a prefix to the name of the parent carbon chain. For example, the following molecules are named as 2-methyl-prop-1-ene, 3-methyl-but-1-ene respectively. In higher alkenes, molecules can be arranged in more than one way. For example, the molecule of alkene with 4 carbon atoms, that is C4H8, can either be arranged as but1-ene, but2-ene, or 2-methyl-prop-1-ene. These are called structural isomers. In addition to this, it is observed that C4H8 shows 2 distinct special arrangements. They are cis-2-butene and trans-2-butene. These are called stereoisomers. Thus, higher alkenes are said to show both structural and stereoisomerism. In structural isomerism, they show chain and position isomerism. In stereoisomerism, They show geometrical or cis-trans isomerism. In a molecule of C4H8, all the carbon atoms are present in the form of straight or branched chains. For example, structures 1 and 2 have straight chains, whereas structure 3 has a branched chain. Structures 1 and 3 and 2 and 3 are said to be chain isomers of each other. When in two structures, the position of the double bond alone is different, they are said to be position isomers. Structures 1 and 2 are position isomers. A compound like but2-ene shows two distinct configurations or spatial arrangements, and hence, its molecules are said to show geometrical isomerism, a type of stereoisomerism. When the two CH3 groups attached to each carbon atom of the double bond are on the same side, the isomer is called a cis isomer. On the other hand, when the two CH3 groups attached to each carbon atom of the double bond are on the opposite side, the isomer is called as trans isomer. Due to the difference in the spatial arrangement, cis and trans isomers have different melting points, boiling points, dipole movement, solubility, and many other properties. For example, the cis but2-ene molecule is polar, whereas the trans but2-ene molecule is non-polar. This is because in a cis but2-ene molecule, as the two CH3 groups are on the same side of the double bond, there is a greater, hence the molecule is polar, CH3 bond dipole on each side, causing distinct positive and negative regions in the molecule. However, in case of a trans but2-ene molecule, the two CH3 groups are present on the opposite sides of the double bond. Thus, the bond dipoles of each CH3 bond cancel each other, making the molecule non-polar. Hence, we can conclude that trans isomers are more stable than cis isomers. Alkenes can be prepared from alkynes, alkyl halides, vicinal dihalides, and alcohols. Let's look at each of them in detail. To obtain alkenes from alkynes, we carry out partial catalytic hydrogenation. During this reaction, addition of a hydrogen molecule, that is, addition of two hydrogen atoms, takes place across the triple bond of the alkyne. There are two catalysts that are commonly used. One is palladized charcoal, which is partially deactivated using compounds like barium sulfate or quinoline. It is also known as Lindlar's catalyst. The other catalyst is sodium in liquid ammonia. For example, ethine, on reduction with palladized charcoal or sodium in liquid ammonia, forms ethane. Similarly, propine, on reduction with palladized charcoal or sodium in liquid ammonia, forms propene. Depending upon the nature of the catalyst used, a higher alkyne can be reduced to cis or trans alkene. Lower alkynes, such as ethine, and propyne and higher terminal alkynes do not yield cis-trans isomers upon hydrogenation. When the catalyst used is Lindlar's catalyst, the alkene obtained shows cis geometry. When the catalyst used is sodium in liquid ammonia, the alkene obtained shows trans geometry. For example, 2-butene on reduction with palladized charcoal in presence of quinoline forms cis-2-butene. However, 2-butene on reduction with sodium in the presence of liquid ammonia forms trans-2-butene. Alkenes can also be obtained from dehydrohalogenation of alkyl halides. When an alkyl halide is heated in presence of alcoholic potash, it gives an alkene and one molecule of halogen acid is eliminated in the reaction. The hydrogen atom for the halogen acid is obtained from the carbon atom adjacent to the carbon atom attached to the halogen atom. The carbon atom attached directly to halogen is called alpha carbon, whereas the adjacent carbon is called beta carbon. Hence, the reaction is known as beta elimination reaction. As hydrogen and halogen atoms are removed in the form of halogen acid from alkyl halide, the reaction is also known as dehydrohalogenation reaction. For example, 1-chloroethane on heating with alcoholic potassium hydroxide forms ethene. During this reaction, the hydrogen and halogen atoms on adjacent carbon atoms of 1-chloroethane are eliminated in the form of hydrochloric acid. In a dehydrohalogenation reaction, if there are two possible positions where the double bond can be formed, then the product obtained is governed by Saint-Zeff's rule. Saint-Zeff's rule states that elimination would predominantly proceed to the formation of olefin in which the double bond is highly substituted. In other words, the hydrogen atom will be removed from the carbon atom possessing lesser number of hydrogens. The rate of reaction depends on the nature of alkyl group and the halogen respectively. The rate increases from primary to tertiary alkyl halides as shown here. The rate is also affected by the halogen atom attached and is the highest for iodine and lowest for chlorine. Another way to obtain alkenes is by the dehalogenation of vicinal dihalides. In vicinal dihalides, the two halogen atoms are attached to two adjacent carbon atoms. When such dihalides are treated with zinc metal, the zinc atom removes the two halogen atoms, forming zinc halide, leaving behind an alkene in the process. This reaction is also called dehalogenation, as zinc removes two halogen atoms simultaneously. For example, when dibromoethane is treated with zinc, it forms ethene and zinc bromide. And when 1,2-dibromopropane is treated with zinc, it forms propene and zinc bromide. Alkenes can also be obtained from alcohol using acidic dehydration process. When heated with concentrated sulfuric acid the OH group of the alcohol and one hydrogen atom from the adjacent carbon atom are eliminated in the form of a water molecule, forming an alkene. Hence, the reaction is said to be acidic dehydration of alcohol. An example of this would be the dehydration reaction of ethanol on heating with concentrated sulfuric acid to form ethene. During this reaction, the hydrogen atom and the hydroxyl group from adjacent carbon atom are eliminated in the form of water to form ethene. Dehydration takes place in 3 stages. First, the alcohol is protonated by the acid catalyst to form a protonated alcohol. Secondly, the protonated alcohol loses a water molecule to give a carbocation. Finally, the carbocation formed loses a hydrogen ion and forms a double bond. Satzev's rule also governs the dehydration of alcohols. For example, in the dehydration of 2-butanol, there are 2 possible positions for the double bond. However, 2-butene is more substituted than 1-butene. Hence, the more predominant product is 2-butene. Thus, we see that alkenes can be obtained by many different methods. Now let us look at the physical properties of alkenes. Alkenes are colorless hydrocarbons. Except for ethene, all the other alkenes are odorless as well. The first 3 members of alkene homologous series are gases, the 4th to 14th are liquids, and all members above 15th are solids. Being non-polar compounds, alkenes are insoluble in water, but soluble in non-polar solvents like benzene and petroleum ether. Alkenes are unsaturated hydrocarbons consisting of a sigma bond and a pi bond. The typical reactions of alkenes involve the breaking of the weak pi bond to form 2 sigma bonds. Such reactions are called addition reactions. These addition reactions are usually electrophilic in nature, as the pi electrons of carbon-carbon double bond are available to any species seeking electrons. Let us study the following reactions in alkenes. Addition of dihydrogen, addition of halogens, addition of halogen acid, addition of sulfuric acid, addition of water, oxidation, ozonolysis, polymerization. Let's start with addition of dihydrogen to alkene. Alkenes react with dihydrogen in the presence of catalysts like finely divided nickel, palladium, or platinum to form alkanes. Such addition reactions are always cis addition reactions. For example, ethene in the presence of finely divided nickel, palladium, or platinum yields ethane. Similarly, propene yields propane. Now let's look at the addition of halogen to an alkene. Alkenes react with halogens such as chlorine and bromine to form vicinal dihaloalkanes. However, they don't react with iodine under normal conditions. For the reactions with chlorine and bromine, the alkenes and the halogens are mixed together in an inert solvent like carbon tetrachloride. Ethene reacts with bromine to give 1,2-dibromoethane. This reaction proceeds via the formation of an intermediate called cyclic bromonium ion. During the addition reaction between ethene and bromine, the reddish-brown color of bromine gets decolorized due to the formation of dibromoethane. Hence, this reaction is used as a test for unsaturation. Let us now look at the addition of halogen acid. Alkenes react with halogen acids to form haloalkanes. In the reaction with alkenes, hydrogen iodide is more reactive than hydrogen bromide, which is more reactive than hydrogen chloride. In the case of symmetrical alkenes, only one product is formed. For example, ethene on reaction with hydrogen bromide gives bromoethane. Or 2-butene with hydrogen bromide gives 2-bromobutane. However, in the case of unsymmetrical alkene, two products are formed. For example, propane reacts with hydrogen bromide to form 2-bromopropane and 1-bromopropane. Of these, 2-bromopropane is a major product. This is in accordance with Markovnikov's rule, which states that during the addition of an unsymmetrical reagent to an unsymmetrical alkene, the negative part of the addendum is added to that unsaturated carbon which possesses lesser number of hydrogen atoms. In the reaction between propene and hydrogen bromide, hydrogen bromide provides the electrophile H+ that attacks the carbon-carbon double bond, leading to the formation of primary and secondary carbocations. The secondary carbocation, being more stable, is formed readily. This secondary carbocation is attacked by the bromide ion to form 2-bromopropane. Hence, 2-bromopropane is a major product. However, the addition of hydrogen bromide to unsymmetrical alkenes like propene in the presence of peroxide is on the contrary to Markovnikov's rule and is known as anti-Markovnikov's addition or peroxide effect or Kharash effect, as it was first observed by M.S. Kharash and F.R. Mayo in 1933 at the University of Chicago. The peroxide effect takes place via the free radical mechanism. In this reaction, initially benzoyl peroxide undergoes homolysis to form benzene free radical. This attacks hydrogen bromide and results in the generation of a bromine free radical. This bromine free radical further propagates the reaction by attacking the double bond in propane. Hence, propane undergoes homolytic cleavage to produce less stable primary and non-stable secondary free radicals as shown here. The secondary free radical attacks hydrogen bromide to form bromopropane, and the primary free radical attacks hydrogen bromide to form 2-bromopropane. Thus, 2-bromopropane is formed as the major product. Now let us move to the addition reactions of alkene with sulfuric acid and water respectively. Alkenes react with cold concentrated sulfuric acid in accordance with Markovnikov's rule to form alkyl hydrogen sulfates. For example, ethene and propene react with cold concentrated sulfuric acid and form ethyl hydrogen sulfate and propyl hydrogen sulfate respectively. Alkenes react with water in accordance with Markovnikov's rule. In the presence of concentrated acids like sulfuric acid, a water molecule adds to an alkene molecule across the double bond to form alcohol. For example, 2-methylpropene reacts with water in presence of concentrated sulfuric acid to form 2-methylpropan-2-ol. Let us now look at the oxidation reactions of alkenes. Alkenes, on reacting with cold dilute aqueous solution of potassium permanganate, which is also called Bayer's reagent, produce vicinal glycols, that is, 1,2-diols. For example, ethene, on reaction with Bayer's reagent, forms ethane 1,2-diol or ethylene glycol. As the purple color of potassium permanganate decolorizes with the formation of glycol, this reaction is used as a test for unsaturation. Depending on the nature of alkene and experimental conditions, alkenes react with oxidizing agents such as acidic potassium permanganate or acidic potassium dichromate to form ketones or acids. For example, 2-methylpropene, on reacting with acidic potassium permanganate, gives propan-2,1 or acetone. On the other hand, but-2-ene, on reacting with acidic potassium permanganate, gives ethanoic acid. Let us now look at the addition of ozone to an alkene, which is also called ozonolysis. Alkenes react with ozone to form ozonides, which, on further hydrolysis, in the presence of zinc, form either aldehydes or ketones or both. For example, in this reaction, the ozone molecule is added across the double bond in ethene to give ethene ozonide. This, on hydrolysis, forms formaldehyde or methanol. The oxidation of alkenes by ozone to form ozonides, followed by its decomposition with water, is termed as ozonolysis. This reaction is useful in locating the position of the double bond in an unsaturated molecule. Let us look at another example of ozonolysis reaction of propene. Here, first propene and ozone react to form propene ozonide. The propene ozonide, on further hydrolysis, in the presence of zinc, undergoes cleavage to form ethanol and methanol. The products formed helps us to determine the position of the double bond in propene as shown here. Let us move on to the last reaction, that is, polymerization. Alkenes undergo addition polymerization reaction when heated under pressure in the presence of suitable catalysts. In this, a large number of molecules of the same species join together to form a giant molecule called a polymer. The simple compound which forms the polymers are called monomers. For example, ethene, when heated to 1000 degrees Celsius under 1000 atmospheric pressure, undergoes polymerization to form polythene. Aromatic hydrocarbons containing two or more fused rings are called polycyclic aromatic compounds or polynuclear aromatic hydrocarbons. Coal tar is the main source of polynuclear aromatic hydrocarbons. These hydrocarbons possesses either a linear or an angular structure. An example of a hydrocarbon with a linear structure is naphthalene or anthracene, and that of with an angular structure is phenanthrene and pyrene. These hydrocarbons are carcinogenic. That is, they cause cancer. Examples of polynuclear hydrocarbons that cause cancer are 1,2-benzanthracene, 3-methylchloranthrene, 1,2-benzpyrene, 9,10-dimethyl 1,2-benzanthracene, and 1,2,5,6-dibenzanthracene. There is no general method by which we can predict as to which polynuclear hydrocarbons will be carcinogenic. However, it is found that the number and position of certain groups such as methyl, hydroxide, cyanide, and methoxy in these compounds give rise to carcinogenic tendencies. These polynuclear aromatic hydrocarbons enter the environment due to the incomplete combustion of coal, petroleum, tobacco, etc. On entering the human body, these compounds undergo various biochemical reactions and damage DNA. This causes a sudden change in the DNA structure, leading to cancer. The elimination of carcinogens from the environment can reduce the incidence of cancer to a great extent. The group of unsaturated hydrocarbons with the general formula CnH2n-2 is known as alkynes. Alkynes contain at least one triple bond between two carbon atoms. The first of the alkyne series is ethyne, with the chemical formula C2H2. Ethyne, also known as acetylene, is used for arc welding in combination with oxygen gas, which is known as oxyacetylene flame. Alkynes have less number of hydrogen atoms than that of alkanes and alkenes. Hence, though their names are different, the nomenclature of alkynes is invariably dependent on the corresponding alkane. In the IUPAC system, alkynes are named by replacing the ANE of the corresponding alkanes by the suffix YNE. For example, ethane becomes ethyne and propane becomes propyne. In a structure, the carbon atom with the triple bond is assigned the lowest number. This lowest possible number of the carbon atom also denotes the position of the triple bond. However, in some alkynes, there may be more than one possible structure because the position of the triple bond may be different in each structure. For example, pentyne has two structures, as shown here. In one structure, the position of the triple bond is 1, whereas in the other, it is 2. They are named as pent-1-ine and pent-2-ine. When two compounds differ in their structures due to the position of their triple bond, they are known as position isomers. Let's see if we can arrange the atoms in a different way to get another different structure. you can see that we got a chain structure of the same compound. Such a structure is known as a chain isomer. In this structure, the position of the triple bond is 1. Therefore, the name of the isomer will be 3-methyl-bute 1-ine. Now let's understand the structure of ethyne molecule in relation to a triple bond. An ethyne molecule has 2 hydrogen atoms bonded to 2 carbon atoms. Each carbon atom has 2 sp hybridized orbitals and 2 unhybridized p orbitals. The head-on overlapping of the 2 sp hybridized orbitals of the 2 carbon atoms forms a carbon-carbon sigma bond. The sp hybridized orbital of each carbon atom overlaps with the 1s orbital of each hydrogen atoms along the internuclear axis. This overlapping forms 2 carbon-hydrogen sigma bonds. The hydrogen-carbon-carbon bond angle is 180 degrees. The unhybridized p orbitals in each carbon atom lie perpendicular to each other as well as to the plane of the CC sigma bond. The 2 p orbitals undergo lateral or sideways overlapping, forming 2 pi bonds between the 2 carbon atoms. Hence, an ethyne molecule consists of 1 carbon-carbon sigma bond, 2 carbon-hydrogen sigma bonds, and 2 carbon-carbon pi bonds. The electron cloud between 2 carbon atoms is cylindrically symmetrical about the internuclear axis. Therefore, the shape of ethyne molecule is linear. The carbon-carbon triple bond is shorter than carbon-carbon double or single bond. As the triple bond is shorter, it is stronger compared to single and double bonds. First, let's look at the industrial preparation of ethyne from calcium carbide. In this method, initially limestone is subjected to thermal decomposition, in which it results in the formation of quicklime. Quicklime obtained is heated to high temperatures with coke to get calcium carbide. When this calcium carbide is subjected to hydrolysis, ethyne or acetylene is formed. Alkynes can also be prepared from vicinal dihalides, that is, 1,2-dihaloalkanes. A vicinal dihalide molecule has 2 halogen atoms, each linked to 2 adjacent carbon atoms. When treated with alcoholic potash, the molecule undergoes dehydrohalogenation. In dehydrohalogenation, first, an atom of halogen on one carbon and an atom of hydrogen present on adjacent carbon in the alkyl dihalide are eliminated as one molecule of hydrogen halide. This results in the formation of alkenyl halide. This alkenyl halide, when treated with a strong base such as sodamide, another molecule of hydrogen halide is eliminated, thus resulting in the formation of an alkyne. For example, when 1,2-dichloroethane is treated with alcoholic potassium hydroxide, forms vinyl chloride, and this, when treated with sodamide, forms ethyne. Do you know why a strong base like sodamide is required for the formation of ethyne from vinyl chloride? As the chlorine atom is directly attached to double-bonded carbon atom in vinyl chloride, it is made highly unreactive. In other words, as the non-bonding electrons of chlorine and the pi electrons of carbon-carbon double bond are in conjugation, the carbon-halogen bond acquires a partial double bond character and the removal of it becomes difficult. Hence, a strong base such as sodamide is required for the removal of hydrogen chloride from vinyl chloride to form ethyne. Alkynes follow the same physical characteristics of their predecessors, alkanes and alkenes. The first three alkynes of the series are gases. The alkynes from the 4th to the 11th in the series are liquids, while the higher ones in the series are solids. All alkynes are colorless and odorless, except ethyne, which has a characteristic smell. The CH bond attached to carbon atom with triple bond in alkynes. Alkynes exhibit some polarity, unlike alkenes and alkenes, which are non-polar. This is because the CH bond in alkynes is slightly polar due to the sp hybridization of carbon. As alkynes are non-polar and water is polar, alkynes are water insoluble. However, they dissolve in non-polar organic solvents like ethers, carbon tetrachloride, and benzene. The melting point, boiling point, and density of alkynes are directly proportional to their molecular masses. Coming to their chemical properties, alkynes exhibit more acidic behavior than alkenes and alkenes. For example, sodium metal reacts with ethyne, forming monosodium ethanide and disodium ethanide. Similarly, propene with one hydrogen atom attached to triple bond carbon atom on reaction with soda amide forms sodium propanide. Sodium metal and sodamide are strong bases and do not react with alkanes or alkenes, as they are not acidic. This shows that alkynes are more acidic in nature than alkanes and alkenes. Let's understand why. The hydrogen atoms in ethyne are attached to the sp hybridized carbon atoms. On the other hand, the hydrogen atoms in ethene and ethane are attached to the sp2 and sp3 hybridized carbon atoms, respectively. The sp hybridized orbitals of carbon atoms in ethyne molecules have 50% of s character and hence the highest electronegativity. These electronegative orbitals attract the shared electron pair of the carbon-hydrogen bond towards the carbon of ethyne to a greater extent than the sp2 and sp3 hybridized orbitals of carbon in ethene and ethane. Therefore, the hydrogen atoms in ethyne can be liberated easily as protons. This makes the hydrogen atoms of ethyne, which are attached to the triply bonded carbon atom, acidic in nature. The addition reactions in alkynes are electrophilic in nature due to the availability of loosely held pi electrons. As alkynes contain a triple bond, during an addition reaction, they add two molecules of dihydrogen, halogen, or hydrogen halides to form a saturated molecule. Vinylic cation is formed as an intermediate during the addition reaction of an alkyne. Whereas alkyl carbocation is formed as an intermediate during the addition reaction of an alkene. As vinylic cation is less stable than alkyl carbocation, alkynes are less reactive towards the addition reactions than alkenes. Hence, the addition reactions of alkynes takes place under drastic conditions when compared to the addition reactions of alkenes. Let's go through some addition reactions of alkynes. An alkyne reacts with two molecules of dihydrogen in the presence of suitable catalysts like finely divided nickel, platinum, or palladium to form the corresponding alkane. For example, propyne reacts with two molecules of dihydrogen in the presence of finely divided nickel as catalyst to form propane. Alkynes form dihaloalkene when treated with one molecule of halogen and form tetrahaloalkane when treated with two molecules of halogen. For example, when ethyne reacts with one molecule of bromine, it forms 1,2-dibromoethene. And when it reacts with two molecules of bromine, 1,1,2,2-tetrabromoethane is formed. The reddish-brown color of bromine decolorizes due to the formation of saturated 1,1,2,2-tetrabromoethane. Thus, this reaction is used as a test for unsaturation. Alkyne, when treated with two molecules of hydrogen halide, forms gem dihalide. On the other hand, when treated with one molecule of hydrogen halide, it forms alkenyl halide. Addition in unsymmetrical alkynes takes place in accordance with Markovnikov's rule. This rule says that in an electrophilic addition reaction, the negative part of an addendum attaches itself to the unsaturated carbon atom of the molecule having lesser number of hydrogen atoms. For example, propyne reacts with two molecules of hydrogen bromide and forms 2,2-dibromopropane in accordance with Markovnikov's rule as shown here. Like alkanes and alkenes, alkynes are also immiscible and do not react with water. However, in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius, alkynes add one water molecule to give aldehydes or ketones. For example, ethyne reacts with a water molecule in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius to give ethanol. Similarly, propyne reacts to give propanone. Polymerization is of two types: linear polymerization and cyclic polymerization. When heated in the presence of a catalyst, alkynes undergo polymerization. In linear polymerization, the alkyne molecules form a long chain polymer. For example, linear polymerization of ethine produces polyacetylene or polyethine. Polyethine is a high molecular weight polyene which consists of repeating units as shown here. The polyethine molecule is represented as shown. It conducts electricity under special conditions. This is why a thin film of polyethine is used as an electrode in batteries. In cyclic polymerization, alkyne molecules add to each other, resulting in the formation of a cyclic compound. For example, when ethine is passed through a red-hot iron tube at 873 Kelvin, it undergoes cyclic polymerization. In this cyclic polymerization, 3 molecules of ethine polymerize to form benzene. Because of their polymerization abilities, alkynes combine to form many different compounds. For example, benzene obtained by the polymerization of acetylene is used for the preparation of dyes, drugs, and a large number of other organic compounds. Aromatic hydrocarbons are so named as they possess a pleasant smell. Hydrocarbons containing conjugated cyclic rings are called aromatic hydrocarbons. These aromatic hydrocarbons are also called arenes. Aromatic hydrocarbons can be further classified as benzenoids and non-benzenoids on the basis of the presence or absence of benzene ring. Aromatic hydrocarbons containing isolated or one or more fused benzene rings are known as benzenoid aromatic hydrocarbons. Benzene is the parent compound in benzenoids. It is an aromatic hydrocarbon with 6 carbon-hydrogen bonds arranged in a hexagon. Examples of aromatic hydrocarbons containing fused benzene rings are naphthalene, anthracene, and so on. Certain other aromatic hydrocarbons such as azulene and tropolone, which do not contain benzene ring, are known as non-benzenoids. All 6 hydrogen atoms in benzene are equivalent. Therefore, replacing a hydrogen atom with an alkyl group yields only one type of monosubstituted product. Thus, the monosubstituted products of benzene do not show isomerism. However, when 2 hydrogen atoms of a benzene ring are replaced with 2 similar or different alkyl groups, there is a possibility of formation of 3 isomers. These differ in the position of the alkyl group. Thus, disubstituted product of benzene show position isomerism. The 3 position isomers of a disubstituted benzene are ortho, 1, 2 or 1, 6. Meta, 1, 3 or 1, 5. And para, 1, 4. Thus, the 3 position isomers of dimethyl benzene or xylene are 1,2-dimethyl benzene or orthoxylene, 1,3-dimethyl benzene or metaxylene, and 1,4-dimethylbenzene or paraxylene. Benzene, with the molecular formula C6H6, was first isolated by Michael Faraday in 1825. Due to its characteristic properties and unusual stability, the determination of the actual structure of benzene took many years. The following key facts were taken into consideration to determine the structure that we have today. The ratio of carbon to hydrogen in benzene is the same. That is, 1:1, which is evident from its molecular formula C6H6. This fact tells us that it is a highly unsaturated compound. When benzene is treated with ozone, it forms triozonide. The formation of triozonide indicates that it has 3 double bonds. Further, it produces only one monosubstituted derivative, which indicates that all its 6 carbon and hydrogen atoms are equivalent. On the basis of these facts, in 1865, Friedrich August Kekulé gave the first insight into the structure of benzene. He proposed a structure in which the 6 carbon atoms were arranged to form a hexagonal ring with each carbon atom carrying 1 hydrogen atom. The structure had alternate single and double bonds. The structure of benzene suggested by Kekulé is now known as the Kekulé's structure. However, Kekulé's structure could not explain all the properties of benzene. For example, this structure cannot explain the observed bond length of carbon-carbon bonds, which is 139 picometers. According to this structure, 2 bond lengths are expected due to the presence of alternate single and double bonds. They are 154 picometers due to carbon-carbon single bonds and 133 picometers due to carbon-carbon double bonds. This structure cannot explain the formation of only 1,1,2-disubstituted benzene, because, according to this structure, 2 isomeric 1,2-disubstituted benzenes should result. For example, as shown here, in isomer 1, the 2 chlorine atoms are attached to carbon-carbon single bond, whereas in isomer 2, the 2 chlorine atoms are attached to carbon-carbon double bond. Hence, there is a possibility of 2 isomeric 1,2-dichlorobenzenes. However, experimentally only one 1,2-dichlorobenzene product is obtained. To explain this, Kekulé proposed 2 interchangeable isomeric structures for benzene. These structures are obtained by interchanging the positions of the double bonds, which happens due to the delocalization of the pi electrons between the 6 carbon atoms in the benzene ring. However, Kekulé's structures alone do not explain the unusual stability and the characteristic substitution reactions of benzene. This peculiar behavior of benzene is explained by considering the concept of resonance in Kekulé's structures. We have already learnt that if a molecule that can be represented by 2 or more structures, and these structures differ only in the arrangement of electrons, then the molecule is said to be in resonance, and the set of several possible structures are called resonance structures, or canonical structures, or canonical forms. Any 2 resonating structures are represented by inserting a double-headed arrow between them. These are the resonance structures or canonical structures of benzene. The actual structure of benzene is a hybrid of these 2 resonance structures. It is called a resonance hybrid. This resonance hybrid is more stable than any of the contributing resonating structures. The resonance hybrid is represented by inserting a circle or a dotted circle in the middle of the hexagonal ring of benzene. The dotted circle in benzene represents the delocalization of the pi electrons between the carbon atoms. The difference between the energy of any one of the equivalent contributing structure and the energy of the resonance hybrid is known as resonance energy. The resonance energy of benzene is found to be 36 kilocalories per mole. Due to this, the resonance hybrid of benzene is more stable than any one of its equivalent structures. The resonance hybrid explains most of the properties of benzene. Benzene undergoes substitution in preference to addition due to resonance. If benzene undergoes addition reactions, it loses its stability as the product formed is not resonance stabilized and hence is less stable. On the other hand, if benzene undergoes substitution reactions, the resonance stabilized benzene ring is preserved in the product too. Therefore, benzene undergoes substitution reactions. The resonance hybrid of benzene explains the observed bond length. As it is evident from the resonance hybrid of benzene, due to the continuous delocalization of the pi electrons between the carbon atoms, all carbon-carbon bonds are equal, and the carbon-carbon bond length in benzene is intermediate between carbon-carbon single bond and carbon-carbon double bond. Hence, the bond length in benzene is 139 picometers. As all the carbon-carbon bonds are equivalent, it results in the formation of only one 1,2 disubstituted product. In order to understand the structure of benzene in a better manner, let's look at its orbital structure. According to the orbital structure, each carbon atom in benzene undergoes sp2 hybridization. One unhybridized p orbital remains on each carbon atom. Among the 3 sp2 hybrid orbitals, 2 sp2 hybrid orbitals of each carbon atom overlap axially with the sp2 hybrid orbitals of the neighboring carbon atoms, forming 6 carbon-carbon sigma bonds. The third sp2 hybridized orbital of each carbon atom overlaps with the 1s orbital of a hydrogen atom, resulting in 6 CH sigma bonds. Thus, all the carbon and hydrogen atoms in benzene lie in the same plane with the bond angle of 120 degrees. Here, each carbon atom is left with one unhybridized 2p orbital at right angle to the hexagon of the carbon atoms in benzene. We know that the p orbital has 2 equal lobes, one lying above the other below the plane of the ring. These unhybridized 2p orbitals of the carbon atoms overlap each other sideways as shown here. As there is equal probability of p orbital of each carbon atom to overlap with adjacent p orbitals of carbon atoms, it results in the formation of 2 continuous donut-shaped pi electron clouds, one lying above and the other below the plane of the carbon atoms. This delocalized pi electron cloud makes the benzene more stable than the hypothetical cyclohexatriene. Hence, this is the resonance hybrid of benzene. We know that the stabilization of benzene takes place due to resonance. which is also responsible for its aromatic character. In 1931, Erich Huckel proposed the modern theory of aromaticity, or aromatic character of compounds. The property of a cyclic polene or cyclic ion with alternate double bonds and delocalized pi electrons to undergo substitution reaction in preference to addition reaction is called aromaticity or aromatic character. Cyclic rings or heterocyclic rings or cyclic ions are said to be aromatic if they show the essential properties such as complete delocalization of the pi electrons, planarity, and presence of 4n plus 2 pi electrons in the ring. Let's discuss each in detail. Let us look at the first essential property that is required. The molecule should contain a cyclic cloud of delocalized pi electrons. For delocalization of pi electrons, the ring must be planar to allow cyclic overlap of the p orbital. Therefore, for a molecule to be aromatic, the ring must be planar. Now, let us look at another essential property. For aromaticity, a cyclic compound must contain a total of 4n plus 2 pi electrons, where n is an integer, which can be equal to 0, 1, 2, 3, and so on. This means, for a compound to show aromaticity, it must be planar or cyclic, and it should have delocalized 4n plus 2 pi electrons. This is known as the Huckel's rule. Thus, according to Huckel's rule, the aromatic compounds should have a delocalized electron cloud of pi electrons, such as 2, 6, 10, 14 electrons. The example of aromatic compounds are benzene with 6 pi electrons, naphthalene with 10 pi electrons, and anthracene with 14 pi electrons. When n is equal to 1, 2, 3, respectively. Benzene was first isolated by Michael Faraday. In 1845, August Wilhelm Hofmann and his team isolated benzene from coal tar. Commercially, benzene is isolated from coal tar by subjecting it to fractional distillation. However, we can also prepare benzene in the laboratory by several methods. Cyclic polymerization of ethyne, decarboxylation of aromatic acids, reduction of phenol. Let's look at the cyclic polymerization method. Benzene was first synthesized by Marcellin Berthold by passing ethyne through a red-hot iron tube at 873 Kelvin. In a laboratory, benzene can also be obtained by the decarboxylation of aromatic acids. Sodium benzoate, on heating with a decarboxylating agent, that is, soda lime, loses carbon dioxide and forms benzene. Benzene can be prepared by the reduction of phenol by passing its vapors over heated zinc dust. Next, let's learn about the physical properties of benzene. Benzene is a colorless liquid with a characteristic smell. The boiling point of benzene is 80 degrees Celsius. Due to its non-polar nature, benzene is insoluble in water, but soluble in organic solvents such as alcohol and ether. Benzene is highly inflammable. It burns with a sooty flame due to its high carbon-to-hydrogen ratio. Thus, in general, aromatic compounds that produce sooty flames are distinguished from aliphatic compounds that produce non-sooty flames. If we take a closer look at the orbital structure of benzene, we find that the cyclic, delocalized pi electron cloud is loosely held above and below the plane of the benzene ring. The resonance stabilization of benzene is due to the delocalization of these pi electrons. This structural arrangement makes the loosely held pi electrons available for electrophiles, the electron-seeking reagents. Thus, the substitution reactions in benzene are electrophilic in nature. Hence, we can conclude that benzene undergoes typical electrophilic substitution reactions due to the retention of resonance stabilization of the ring, that is, aromaticity. Some common electrophilic substitution reactions of benzene are halogenation, nitration, Friedel-Crafts alkylation, Friedel-Crafts acylation, and sulfonation reaction. Before we proceed into the detailed study of each type of reaction, let us have a look at the mechanism of a general electrophilic substitution reaction. A general electrophilic substitution reaction involves 3 steps. They are generation of the electrophile, formation of carbocation, a sigma complex intermediate, and removal of proton from the carbocation sigma complex. Now, let's take a closer look at each type of electrophilic substitution reaction along with the mechanism in detail. First, let us take up halogenation reaction. The replacement of a hydrogen atom by a halogen atom such as fluorine, chlorine, bromine, and iodine in a benzene ring is called halogenation of benzene. Let us discuss chlorination and bromination, which occur at a temperature between 310 and 320 Kelvin. Usually, the halogenation takes place in the presence of a Lewis acid such as anhydrous aluminium chloride or ferric chloride or ferric bromide, as they help in the generation of electrophile, that is, halonium ion. When benzene is treated with chlorine in the presence of anhydrous aluminium chloride, it results in the formation of chlorobenzene. Let us discuss the mechanism of this reaction. First, an electrophile, that is, chloronium ion in this case, is generated when anhydrous aluminium chloride combines with the attacking reagent chlorine, as shown here. In the second step, chloronium ion attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or rhenium ion. The sigma complex, which is stabilized by resonance, is shown here. Note that the second step is always a slow step or a rate-determining step, as the aromaticity is lost with the formation of sigma complex. This is because in the sigma complex, one of the carbon is sp3 hybridized and the delocalization of electrons is not possible. In the last step, the proton is removed from the intermediate sigma complex in the presence of nucleophile AlCl4- ion. This results in the formation of chlorobenzene. Note that the last step of the reaction is always a fast step, as the non-aromatic sigma complex is converted to aromatic compound. Now let us look at nitration. When a hydrogen atom in the benzene ring is replaced by a nitro group, it is known as nitration. Nitration is carried out by heating benzene at about 330 Kelvin with the nitrating mixture consisting of concentrated nitric acid and concentrated sulfuric acid. When benzene is treated with nitrating mixture, it results in the formation of nitrobenzene. Let's discuss the mechanism of this reaction. First, an electrophile, that is, the nitronium ion here, is generated when sulfuric acid transfers a proton to nitric acid, as shown in these reactions. The reaction between sulfuric acid and nitric acid is an acid-base reaction in which relatively stronger acid, sulfuric acid, acts as an acid, whereas nitric acid, which is relatively a weaker acid, acts as a base. In the second step, nitronium ion attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or rhenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of the nucleophile HSO4- ion. This results in the formation of nitrobenzene. Now let's look at Friedel-Crafts alkylation reaction. When the hydrogen atom in a benzene ring is replaced by the alkyl group, it is known as alkylation reaction. When benzene is treated with alkyl halide in the presence of anhydrous aluminium chloride, it forms alkyl benzene. This reaction is known as the Friedel-Crafts alkylation. For example, when benzene is treated with methyl chloride in the presence of anhydrous aluminium chloride, it results in the formation of methyl benzene or toluene. Similarly, benzene reacts with ethyl chloride in the presence of anhydrous aluminium chloride to form ethyl benzene. Let's discuss the mechanism of this reaction. First, an electrophile, which is a carbocation here, is generated when anhydrous aluminium chloride combines with the attacking reagent ethyl chloride, as shown here. In the second step, the carbocation attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or arenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of the nucleophile Cl- ion. This results in the formation of ethyl benzene. It is important to note that in Friedel-Crafts acylation reaction, when benzene reacts with N-propyl chloride, isopropyl benzene instead of N-propyl benzene is formed. This is due to the fact that the less stable primary carbocation formed in this step rearranges to a more stable secondary carbocation. Hence, is the result. Now let's look at the acylation reaction. When the hydrogen atom in a benzene ring is replaced by the acyl group, it is known as acylation reaction. When benzene is treated with acyl halide or acid anhydride in the presence of anhydrous aluminium chloride, benzene forms acylbenzene. This reaction is called the Friedel-Crafts acylation. For example, when benzene is treated with acetyl chloride in the presence of anhydrous aluminium chloride, it forms acetophenone and hydrochloric acid. Let's discuss the mechanism of this reaction. First, an electrophile, that is, the acylum ion here, is generated when anhydrous aluminium chloride combines with the attacking reagent acetyl chloride, as shown here. In the second step, acylum ion attacks the pi electron cloud of the benzene ring and forms the less stable intermediate called sigma complex or arenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of nucleophile AlCl4- ion. This results in the formation of acetophenone. Similarly, benzene reacts with acetic anhydride in the presence of anhydrous aluminium chloride and forms acetophenone and acetic acid. Next is sulfonation reaction. When the hydrogen atom in a benzene ring is replaced by the sulfonic acid SO3H group, it is known as sulfonation. Usually, sulfonation reaction is carried out by heating benzene with fuming sulfuric acid or oleum, a concentrated solution of sulfur trioxide in sulfuric acid. Sulfonation can also be carried out by treating benzene with chlorosulfonic acid. Note that during electrophilic substitution reactions, if an excess of electrophilic reagent is used, then further substitution reaction may occur in which the other hydrogen atoms of benzene may also be successively replaced by the electrophile. For example, benzene on treatment with an excess of chlorine in the presence of anhydrous aluminium chloride in the dark gives hexachlorobenzene. Let's move on to the next type of chemical reaction. Addition reaction. Addition reactions occur under drastic conditions at high temperature and pressure. For example, benzene reacts with hydrogen in the presence of a catalyst such as nickel or platinum at 473 to 573 Kelvin under pressure to form cyclohexane. Benzene reacts with chlorine or bromine in the presence of ultraviolet light to form benzene hexachloride or BHC. BHC is used as an insecticide and sold under the names of gamma-axane or lindane or 666. Next, let's discuss the oxidation or combustion reaction of benzene. Usually, aromatic hydrocarbons are stable and not readily oxidized. Hence, on heating in the presence of air or oxygen, benzene burns to produce carbon dioxide and water along with the sooty flame. The presence of higher carbon content than the hydrogen content in benzene produces the sooty flame. Moreover, this sooty flame test is used as an identification test to distinguish aromatic from aliphatic compounds. As we know, benzene undergoes typical electrophilic substitution reactions and forms monosubstituted benzene as the product. When this monosubstituted benzene is subjected to further electrophilic substitution, it forms 3 possible disubstituted products in varying amounts. The disubstituted product formed in major amounts depends on the reactivity of the monosubstituted benzene. In turn, the reactivity of the monosubstituted benzene depends on the nature of the group that is present on the ring. A group can be either electron-releasing or electron-withdrawing. The group present on the ring orients the new incoming electrophile to any of the remaining 5 positions. Of these 5 remaining positions, with respect to position 1, position 2 and 6 are equivalent and said to be the ortho positions. Positions 3 and 5 are equivalent and said to be the meta positions. And the position 4 is said to be the para position. The position that the incoming electrophile will occupy depends upon the availability of electron density in the ring, which, in turn, again depends on the nature of the group G, already present in the benzene ring. This is known as the directive influence of a group. This influence could either be ring activating or ring deactivating. Ring activating groups are plus R groups or electron-releasing groups which make the electron density relatively rich at ortho and para positions of the ring. Hence, these groups orient the new incoming electrophile to ortho and para positions. Ring deactivating groups are minus R groups or electron-withdrawing groups which relatively decrease the electron density at ortho and para positions of the ring. In other words, the electron density is relatively high at meta position. Hence, these groups orient the new incoming electrophile to meta position. For example, the hydroxyl group in phenol, due to the minus inductive effect, withdraws the electron from the ring. Hence, ideally, the electron density at ortho and para positions should relatively decrease. But it is found that the electron density at ortho and para positions is relatively more. This is because of the plus resonance effect, which overweighs the minus inductive effect. Thus, the reactivity is predominantly controlled by the plus resonance effect of hydroxyl group. Due to the plus resonance effect of hydroxyl group, the ring gets activated and the incoming electrophile is directed to the ortho and para positions. The following resonance structures of phenol show that the electron density is much concentrated at ortho and para positions than that at the meta position. Thus, ring-activating groups are said to form ortho and para-substituted compounds in major amounts. Other ring-activating groups include NH2, NHR, NHCOCH3, OCH3. Ortho and para-directing groups facilitate electrophilic substitution by increasing electron density on the benzene ring and are called ring-activating groups. On the other hand, the nitro group in nitrobenzene, due to the minus resonance effect, withdraws the electrons towards itself. Thus, the electron density in the ring decreases. Due to the minus resonance effect of nitro group, it becomes difficult for the ring to undergo further electrophilic substitution reactions. Therefore, the ring is said to get deactivated. In the presence of the nitro group, the electron density at meta position is comparatively higher than the electron density at other positions, and thus the incoming electrophile is directed to the meta position. The following resonance structures of nitrobenzene shows that the electron density is less concentrated at ortho and para positions than that at the meta position. Thus, the incoming electrophile is directed to the meta position. Thus, ring deactivating groups are said to form meta-substituted compounds. Other ring deactivating groups include CN, CHO, COR, COOH, COOR, and SO3H. Thus, we see that the type of group present on the benzene ring influences further substitution reactions in it.